Um,
Starting now.
yeah, but start maybe, yeah.
Okay. Hey everyone. Today we will have Andrew here to introduce the basic dynamical codes, and he's going to do a recap on the regular subsystem code, and and then move to the dynamical version. So let me hand over to Andrew. Andrew, let's go on.
All right. Awesome. Yeah. So as Dean mentioned, I'm gonna talk about dynamical codes. If you don't know what that is, that's fine because I'm gonna start from the basics and how these codes are related to the subsystem codes, which Derek has covered in the past two sessions. Uh, just do this. Um, yeah. So just a quick reminder what error correction is. So you encode your quantum state into some higher dimensional system, and then some noise happens, and then you do bunch of measurements, which you get information on whether any errors had occurred and which appropriate correction operation to do to get your original state. Um, just again, I'm gonna just recap the story code, which you probably seen like hundreds of times in the previous sessions. So yeah, so we tessellate the surface of this torus and we put like this lattice on the surface, and then you put qubits on the edges, and then you do this 4-qubit z measurements on the faces, x 4-qubit x measurements on the vertices. Then my stabilizer codes is just all quantum states that are plus one eigenstates of all these measurement operators. And here everything, all the measurement check measurements commute. But in subsystem code, you have non-commuting check measurements. So if I just take the same lattice that you've seen before for the toric code, and I add qubits on the vertices, I can get the subsystem toric code if I define this 3-qubit x and z measurements on this blue and red triangles. And well, you can see here like this z measurement anti-commute with x measurements that share 1 qubit with it. Trying to get my pen. Yeah, so this guy anti-commute with this guy, right? Because that's the only qubit that they share. Um, and how do I do error correction on this code? So I cannot measure like this non-commuting x and z simultaneously because they anti-commute. But now I don't have the same stabilizers. So my stabilizers now are the product of these two 3-qubit z measurements, and also like this two 3-qubit x measurements. So I have 6-qubit stabilizers. And what I want to do is that I measure x and z alternately, right? So here I measure z, and then I measure x. Like and what I say I measure z means that I measure all this 3-qubit z check measurements, right? And if I take the product of this 3-qubit z and this 3-qubit z, the outcomes of those two, then I'm going to get the outcome of this big 6-qubit z measurement, right? So that's what you need to do, like to do error correction in subsystem codes, which probably Derek has covered last week and the week before. But now I'm gonna introduce like a new example of a subsystem code. This one's called the Kitaev's honeycomb model, which was proposed almost 20 years ago by Kitaev in this paper. Um, so what happens here is that I put this hexagonal lattice on my torus, so we're still working with torus here. And I put my qubits on the vertices of this hexagonal lattice, right? So like this little dots there. And then my measurements are this 2-qubit measurements on the edges. So I have this green edge, red edge, and blue edge, and they correspond to this 2 qubits X, Y, and Z measurements. And now what are my stabilizers? My stabilizers are basically these. So I have this green Z 6 qubit stabilizers. Um, oh, sorry, I think it should be X actually. So it's X, Y, and Z. Sorry about that. Um, and then you can check that all the check measurements anti-commute with some other check measurements, but they commute with all these stabilizers. And I can do the same thing. So what I'm gonna do is going to measure like this 2 qubit check measurements around this plaquette or this hexagon. So what I'm gonna get is that I'm gonna measure like this. What do we have here, right? So we have like this YY and ZZ, right? And since they coincide on 1 qubit, like every coins neighboring edges, then the products of this Y and Z becomes an X. So I'm gonna effectively measure like the 6 qubit X measurements or stabilizers. And yeah, I have to do this over multiple rounds because the checks they don't commute. So if you recall what Derek has covered on this subsystem code, so you must allocate some space for stabilizers, some for gauge qubits, and some the rest for logical qubits. Um, so yeah, so how many stabilizers and gauge qubit and logical qubits this Kitaev subsystem code has, right? So in total we have n qubits. And if you just identify each plaquette with the edges above it, then you can see that I can identify this with that, that with that, and then you see that there are n over 2 plaquette stabilizers. And to count the edges, you can simply see like for each vertex, um, then you have like this X or red edge, and then you have for this vertex you have that edge, this vertex you have that edge, and you can do that for every vertex. You have like 3 edges there that's connected to it. Um, so you have 3n over 2 edges. Um, now, but these checks and these stabilizers are not independent, and that's because you have this if I take the product of all the 6 qubit stabilizers, then I'm gonna get the identity. And so the number of independent stabilizers are and there's also like this one non-trivial loop, right? I can draw like this like this loop there, which yeah, should not use this color, use something else. Yeah, there we go. Yeah, and that's going to be some a stabilizer that's independent of all these plaquette stabilizers, because you cannot create this by taking product of the plaquette stabilizers. um so yeah, so I have this n over 2 minus 1 because I can take one plaquette stabilizers out because the product of all of them um, is the identity. And I have 2 non-trivial loops, right? Because I can draw this guy and one more. in this horizontal direction. Now I have to look for how many independent checks. So if I take the product of all checks, I'm gonna get the identity as well. You can yeah. So if I have like this like if this is XX and this is YY, this is ZZ, then this middle qubit is going to be in the identity. And if you do that for all vertices, then you're gonna get the identity over all n qubits. Um, so I want to take one check measurement out. So I'm gonna get this 3n over 2 independent check measurements. And I'm gonna use like this formula because we have like 2G virtual Pauli operators if we have G gauge qubits, right? And then we want to add that with our stabilizers. So the total number here is what, like 2 G plus R, right? Um, and that must total to this value. And we know what R is from this second point, right? So we can just plug everything in and solve for G, and this is what we get. So yeah, so this first bit, so that's what's that? So I move the 2 to the other side, and then wait, I move R to the other side, and then I divide both sides by 2. So that's what we get. And what does that mean? So how do I compute K? So I'm going to use just subtract G and R from N, and that's what I get. So I just plug in this G and plug in this R to this formula. And unfortunately here we have 0 logical qubits, which kind of suck. But it turns out that um, about I don't know what 15 years later, Hastings and Haah in this paper they realized that, oh, you can actually have logical qubit in this in Kitaev's code, but you cannot view it as subsystem code. You have to view this as a dynamically evolving stabilizer code, which is induced by this, non-commuting green, red, blue, green, red, blue sequence of check measurements. Um, and the fact that there are this red checks are non-commuting with some with the green checks here, that's basically why we have this evolving stabilizer code, right? So after measuring green, we have this stabilizer code as 0, and then measure red, then we get S1, measure blue, get S2, and then measure green, we go back to S0. Um, and over like the rest of this tutorial, basically I'm gonna go towards showing that there are 2 logical qubits there. But first let me go through a simpler example, right? Because this is, it's complicated. You have there's a lot of things going on here. You have a bunch of checks and you have a bunch of stabilizers, but this is way simpler, right? So this is the 412 surface code, and it has 3 stabilizers, right? This 4 qubit Z and 2 qubit X's, right? And I'm gonna write that this way, right? So these are just so this is that top left qubit, top right qubit, bottom right qubit, bottom left qubit. And I'm gonna call this generators. So these are the generators of the stabilizer code, G0, G1, and G2. And these are the logical operators of this surface code. Right. So gonna transform this code to something else. I'm gonna do this measurement, right? I'm gonna do this ZZ measurement. And if you notice, this anti-commutes with this X stabilizers. So we see what's going to happen there. Um, So let's first assume that we start on some arbitrary code state. So I'm just gonna pick some random code state sidebar from the code space of this surface code. Um, and first I'm gonna look at these two generators, right? That anti-commutes with this measurement S prime. And assume that I have this outcome O, which is either +1 or -1, and it's going to be random because it anti-commutes with this operators. Um, so what's my new state going to look like after I measure this S prime with outcome O is that I'm going to project this sidebar um into this projector, right? So that's how the projector is defined when you have outcome O. And okay, so what's going to happen here? So this is my new state, this phi bar. Then what happens if I apply this OS, right? So O is just +/-1, OS prime to this new state sidebar. So I'm gonna have this so that's just the definition of this sidebar, remember, like this guy. And this is the definition of the projector. And as you can see, these are just the same. This is just identity, and this guy is just the same thing, the same Pauli operator. So they commute, right? So I can move like um so I multiply this with that, and I'm gonna get the identity, and I multiply this with the identity, I'm gonna get OS prime, right? So that's gonna be that's just the projector. And that's basically the definition of this updated state. So what this means is that this guy, this new projected state after I measure it, it's stabilized by this OS, right? So just this Pauli observable with the multiplied by the measurement outcome +or -1. Okay, so we're gonna look at the other cases. So the next case is I'm gonna look at this G1 and G2. So if you remember, like G1 is XX on this 2 qubits. Let me just redraw that. Right. So we have this 4 qubits, and that's G1, and we have this XX, and that's G2. So they anti-commute with this S prime. Um, so that's what that means, right? So like my measurement outcome here, like if it's O, if I commute this G1 or G2, similarly to the other side of this projector, then I'm gonna get the minus of that. So now let's check what's going to happen if I apply this G1 to my new state, right? So that's the definition of the new state. That's the definition of the projector. And then I move G1 to the other side, right? And then that's gonna flip the sign, right? And then so G1, if you remember, that's just the stabilizer of the original state psi bar, right? So that's just equal to psi bar. And as you can see, like this is not equal to my new state, right? So it's not stabilized by G1, right? So we can do the similar thing with G2, and you'll find the same thing here. Um, so right, so this phi bar is not stabilized by either G1 or G2 individually, but what about the product of those two, right? So let me define this S3, right? Which is product of G1 and G2. And this is still in the stabilizer of the original code of this of the surface code, this guy, because just the product of these two generators. Um, and then you can see now that this commutes with S prime, right? So S prime is just like this C Z I, right? So it coincides on 2 qubits with this stabilizer, so they commute. it commute with the projector. So if I check if what happens if I apply this S3 to my new state, and I'm gonna write this again, the definition of that new projected state. And now I'm gonna pop in this S3, because you remember S3 is a stabilizer of this code state, right? So I can just put that there. And then because this S3 commute with the projector, I move S3 to the other side. So this becomes the identity. And I'm going to left with this guy, which is just the new projected state. And what this means is that this guy is stabilized by the product between G1 and G2. So I have not looked at this last generator, this 4-qubit Z, and that commutes with S, because S is just, this 2-qubit Z measurements. So Z and Z commute. And okay, what happens if I do this? And I put the definition of that new state again. And I commute G0 to the other side of the projector. And it disappears because it's a stabilizer of this code state. And then I'm just left with this projected state, which is that phi bar. So this new state is stabilized by this 4-qubit Z stabilizer. Okay. Um, so what have we done so far? So we found that this new code state is stabilized by this OS bar. So O is the just plus minus one. And this G0, this 4-qubit Z stabilizer, and product between these two 2-qubit X stabilizers on the sides. So I did not make any assumption of which phi bar that I make. It just needs to be, something inside this code state QS. So therefore, this is true for any code state psi bar. So if I project it using this projector, after I measure S prime and get outcome O, so any updated code state is going to be stabilized by these three operators, right? So I'm just gonna assume that we get a +1 outcome, right? Because it's random, so it doesn't really matter. If it's minus, I just need to adjust accordingly on like this O factor. But the upshot here is that now I have this new stabilizer group S prime, right? And these are generated by these three guys, right? That stabilizes all of my new code states, right? So I kind of like shifted, projected like all my code state from S of this stabilizer um the initial stabilizer code into this new code space which are stabilized by these guys, right? So for just to make this nicer, I'm just gonna change this G0 to that because that's basically the same thing. I take the product between this G0 and S prime, right? So I get like this IIZZ just to make things nicer and more symmetric. You'll see why it's nicer in the next page. So yeah, so basically what we have done is we update this stabilizer group S to S prime after measuring this small S prime. So what does that look like? Oh, actually, yeah, I want to go into like one more thing. So if you remember, these are the logical operators of the original this 412 surface code. And like this X and Z operators have this logical plus and logical zero eigens plus eigenstates and minus eigenstates their minus eigenstates being this logical minus and logical one. Um, so after I measure this, and then I also do an update on these +1 eigenstates. So I'm going to do like the same thing as what I did in the previous slide. And I'm gonna check, if there's still the eigenstates of this x and z. And there actually are. And that's mainly because the measurement that I did, this guy, commutes with both logical x and logical z, right? So I can move this z bar to the other side of the projector, and I get the same um, logical state. It's like this projected logical state is still the +1 eigenstate of this z bar, and the same thing with x bar, right? Um, that's basically what this means, and we're gonna see later what happens if this S prime anti-commute with one of the logical operators. And basically what we've done now, we've switched from this guy to this guy, right? From this left code to the right code, and yeah, that's the reason why I picked like this nice generator, so I can draw it this way, and it's looks nicer. Um, and the reason why I have like this arrow going back and forth is because we can switch back from S prime to S by measuring this guy, right? And basically, I'm just gonna left this as an exercise. You just need to follow like the same steps that I've done like in the previous slides. Um, Pretty much, yeah. And yeah, so what happens if I do this measurements instead, right? This measurement instead of this S prime, right? So I have just two Z's on the bottom. Um, yeah, and you also you, you only need to follow like the steps that I've done previously. So yeah, if I measure these two guys alternately, then I can switch back and forth between these two codes. So if I'm in this code S, that I do this S prime measurement. If I'm in code S prime, then I do this S prime prime measurement to go back to S. Let me stop for a second there, see if there's any question. Okay. Let's see. I don't hear anything, so yeah, let me just proceed to the next thing. So yeah, so this both of these guys have three independent stabilizer generators, right? And so if I do like this formula for how many logical qubits they encode, so I'm gonna subtract this n with 3 because I have three independent stabilizer generators, and n is just 4 because we only have 4 qubits, right? So we have one logical qubits for both of this S and S prime. And yeah, so that's logical. We can pick the same logical representative for S prime. Um, and yeah, so this other another interesting thing. So if we think about these two codes as a subsystem code, right? So I take the gauge group of the subsystem code as the union um, of the two stabilizer groups, right? So it's gonna be generated by just taking the union of the generators of those two stabilizer groups. I think it's a good exercise to kind of like calculate how many gauge qubits or logical qubits the subsystem code has. Um, right. So this is some more general statement. I know this looks very long and scary, but basically we've done all of these in the previous slides. Um well, basically did like this three. So if I start with this stabilizer group S with generators G, um right, this I have this R generators and I'm measure this Pauli measurement P with outcome O, either plus or minus 1. So how do I construct this new stabilizer group S prime? So if plus minus P is in the original stabilizer group, then it's just not it's not very interesting because it's basically a stabilizer. So S prime is just equal to S. But if plus minus P is not in the stabilizer group, but P commutes with all of S, right? So what does that mean? Um, so that means P is in the normalizer or equivalently the centralizer of S, but it's not a stabilizer itself. That means we measured a logical operator. This P basically is a logical operator. So what happens to the new stabilizer group is that we just add this OP, right? Because basically we kind of like fix this logical degree of freedom. So we put that OP into the stabilizer group, right? And that's generally not good because now you're increasing the size of your stabilizers group, and then you decrease the size of your logical space. Yeah, you don't want to do that in general, unless you're doing some computation and you want to measure some you want to do some logical measurements. And this last step three is basically a generalization of what we've seen in this um, stabilizer what do we call this surface code this 4 qubits surface code switching. So if P, this measurement does not commute with this bunch of this generators, then what I'm gonna do is that I'm gonna define this new set, right? So I'm gonna take G1 out of W, and then I multiply G1 with the rest of the elements of W, right? So this is what that means, right? So I multiply G1 with G2, multiply G1 with G3, multiply G1 with all the way to GL. So it has size of L minus 1. And now all the elements of this W prime commute with P, right? And so if we it's basically kind of like give us a different generator of this original stabilizer group S. So it's basically generated by this, right? G1, this W prime, because I can just multiply G1 to elements of W prime and get the elements of W back. Um, and all the rest of generators that commute with P. With this new set of generators, P only anti-commutes with G1. Um, yeah, so now we can just this is how we do the update on the generators. So I put this OP in the set of new generators, and we keep this W prime because it commutes with all the with P, and the rest of the generators also commute with P. So now we're good, and we can construct this S prime, right? So that's basically what we did. If you remember, we multiply this x with this xx. So now it commutes with this ZZ measurement, right? But individually they don't commute with this ZZ, right? So that's basically what this rule 3 is doing in a more general way. Um, yeah, and this is a more general statement for how on how to update the logical operators. So we have like basically these are all connected to the previous stabilizer update rule, right? So the first one, if P is equal to L, right? So this is where we do logical measurement. Was that a question? I'm happy to take a question though, because I think this is quite important. Remove like all these scribbles. Okay, let me just proceed then. Yeah, so this first bit is where you do logical measurement. So yeah, so L is the logical operator of the initial stabilizer group S with this generator. So yeah, I want to update that to some L prime. But if we do like this first case, we're doing like a measurement, a logical measurement. So that means L is now the value of L is now fixed, right? Because we see this outcome O, and we just put it in the new stabilizer group, right? So that's from the previous rule, this guy, rule number 2. Um, and second case is what we've seen in the surface code example in the previous slides. So this measurement P commutes with logical operator L. Therefore, we just keep L as a logical operator for this new updated stabilizer group. And now if P does not commute with L, now what I'm gonna do is but it commute with all the stabilizers in this S. So I'm gonna replace this L with L prime, which is just this OP, right? This P with multiplied by whatever measurement outcome you see after measuring it. And it's now a stabilizer in this S prime. And I'm gonna talk about why that is in a little bit. So the last update rule is where P does not commute with this logical L, and also does not commute with some stabilizers in S, right? And this is related to the stabilizer update rule number 3, because now I want to multiply this uh, L, the old stabilizer logical operator or logical operator with this G1. So this G1 is um the generator that I pick from my generators that does not commute with my measurement, and I throw it away, right? So I throw this G1 away, replace it with OP here. So I'm going to take this same G1 and multiply that um, to this logical operator. Um, okay, so I'm gonna go through rule number 2, 3, and 4, because I think these are the ones that are a bit probably a bit non-trivial. Um so in rule number, well, we've seen this actually. So this logical L commute with P, so it commutes with the projector, right? So I can show that if this J bar is the logical plus one eigenstate of this logical L, then it remains if I project it on this with this measurement projector, then it's still a plus one eigenstate of L, right? So we've seen that. But number for rule number 3. Right. So we're updating this L to L prime, right? So this we just replace this with OP, right? So this is when P does not commute with L but commute with the rest of S, right? And what that means is that P is some other logical operator, right? It's a logical operator, but it does not commute with L. So it's kind of like this because you have this X bar and Z bar, right? So if L is equal to X bar, then this P will correspond to Z bar, right? Because Z and X bar anti-commute. Um, so that's basically what we did in this case where we apply rule number 3. So what we're gonna do here is that if this J bar is the plus one eigenstate of this logical L, then I project that onto depending on which outcome I see, because it's an anti-commute with this L. So it depends on like what logical state do I have at that point. Um, but either way, this is going to be stabilized by plus P or minus P, right? And this is um going to stabilize the new state that I have, right? That's the reason why I add this OP into the new stabilizer group. So the last rule is where I update this to L, this L prime, right? I pick like this G1 that I throw away from my stabilizer group, and then I multiply that with this logical operator that anti-commutes with P, right? So this is I think is quite intuitive. So if you remember, like this G1 is a stabilizer in the original stabilizer group S, right? So G1 is in S. So as we know, a logical operator multiplied by a stabilizer is basically still the same logical operator. It's just a different representative. So this G1L is basically the same logical operator as L. But the reason why I want to multiply this G1 with L is both G1 and L anti-commute with P, right? Because this G1 is the stabilizer that I throw away that because it anti-commutes with P. Um, so now if I look at if this L bar um I want to show that this L bar stabilizes this new projected +1 eigenstate of L, right? So that's the definition of the projected +1 eigenstate. And that's the definition of L prime. And I can move the L to the other side and I flip the sign of the projector. And then I move the G1 to the other side again and I flip projector the sign of the projector again. But now I'm back um, to where I was on this projector. And I can get rid of this L because it's a this J is +1 eigenstate of L, and then this G1 is a stabilizer of this J bar, right? So I can get rid of this G1 and L, and I'm gonna get this, which is the definition of the updated +1 eigenstate of L, right? So therefore this is the +1 eigenstate of L prime. Right. So that kind of justifies why we want to update L to this L prime. I'll stop for there's if anybody has any quick question. Okay. So I'm gonna go back to the Honeycomb Floquet code, right? So I'm just gonna use like this like the smaller lattice to make things simpler, right? So basically what we're gonna have here is that I'm gonna measure the green checks, right? These are the XX checks, and then I'm gonna measure the red ones, and I'm gonna measure the blue ones. And what's going to happen is that I'm going to have this three stabilizer groups, this S0, and then after I measure X, I'm gonna go to S1. After I measure blue, I'm gonna get the blue checks, I'm gonna go to S2, and I'm go back to S0 after measuring the green checks. And this stabilizer groups are gonna be generated by this. So this CG is these are the green checks. This AB are the blue plaquettes. This AG, these are the green ones, and AR are the red ones, right? And the red ones basically have this YY uh, Pauli operators on it, and the green ones has X operators, and the blue ones have Z's. Right, and gonna see why that is in the next slide. So okay, let's say I'm just done with measuring all the green checks. So all the green checks are in my stabilizer group, which is S0. And now I'm going to measure all the red checks. Right, so I'm just going to look at this one blue plaquette. Say it's this one, right? So I have like this green check, and this green check in my stabilizer group S0, right? And first I'm going to measure this guy, right? So that's why I have that number 1 there. And after I measure it, I put that red check into my stabilizer group, and now I'm going to throw away this guy and keep the product of these two green checks, right? So that's why I have this blue shade here. And then this is the second one that I'm gonna measure. That's the third one. This one. So after I measure this second green check, um, so this anti-commute with this big 4 qubit Pauli, and it anti-commute with this 2 qubit Pauli. Therefore, I'm just gonna take the product of both, right? So now I have like this 6 qubit stabilizer. Let's get rid of that. And I also have this two red checks in my stabilizer group now. And then the last one, this red check number 3. So that's going to commute with this, this 6 qubit thing, right? Because it coincides on two qubits. Um, so what that means is that yeah, and now I'm done. And what I basically what I need to do with this is I'm gonna just look at all these blue plaquette stabilizers and do this same steps, right? The same 3 steps. Um, so if you note that now like this 6 qubit stabilizer is a what is it like? So taking the product of green. So these are X stabilizers, right? But that's not what we really want. We want a Y this to be Y. Oh no, sorry, Z. But I can just take the product of these 6 qubit X's with this red Y checks, right? Then I'm gonna get the Z um sorry, it's Y. So I'm gonna get this 6 qubit Z stabilizer. And this is basically this blue plaquette Z stabilizer, right? So this guy here. And basically, after I measure like this green checks and this red white checks on that surround this blue plaquette, like this guys. Um, if I take the product of this 6 2 qubit checks, then basically I'm gonna get the measurement outcome of this Z 6 qubit Z stabilizer, right? So across this 2 rounds, I'm measuring like this blue um 6 qubit stabilizers. Yeah, that's basically what this last bit says. So let's move on. Yeah. So this is yeah, so we just do that for for each round, then we're gonna get this S0, S1, and S2 stabilizer groups. And these stabilizer groups are called instantaneous stabilizer groups because you only see this stabilizer group right after this round 0 check measurements. And then you're gonna see this S1 right after um, round 1 check measurements. And you're gonna get the syndromes of this stabilizers, right? So use this blue plaquettes here and this red plaquettes in this round, and this um green plaquettes here, right? Because this green is a product of the red and blue checks. This blue one's product of green and red checks, and this red one's a product between the green and blue checks. Right. And these stabilizers are there in in the intersection of all of this 3 groups. So now I've told you that this actually encodes 2 logical qubits, and we're gonna see why. Um, Yeah, it's gonna take quite a few steps. Kind of running out of times, but basically, like the idea is it's pretty much similar. Um, okay, so if you recall, so we if we have n qubits in this honeycomb lattice, we have n by 2 plaquettes and 3n by 2 edges. So I have like this red, green, and blue plaquette stabilizers, and I have n over 2 of them. Say I'll just look at this stabilizer as 0, right? So I have the green checks. And the green checks are only on 1/3 of all the edges, right? Because I have 3 colors. So the number of the edges with green color is just n over 2. And again, I'm going to use the fact that the plaquette stabilizers are not independent because the product of all of them is the identity. So I can remove just one of them. So there are n over 2 independent plaquette stabilizers. Yeah, you can take all of them and just take out a green plaquette or something. Um, Now I'm gonna note also that if I take the product of this green checks and the remaining plaquette stabilizers, um, this is also not independent because this green checks like they're like this XX checks, and if you I'll just go back to the figure. So this green checks, this is XX, and if I take the product of this and this two X plaquettes, right? So this have um 6 qubit X stabilizers. So this qubit is going to be identity. It's going to be identity. And like also like all these vertices that connect that are on both green plaquettes and green edges. They're going to be identities. So I can just take one green check out, right? So I have n over 2 independent green checks. Now I can calculate the number of independent stabler generators. I just add this guy with this guy, right? So I have this n minus 2. And now I can use this formula to compute number of logical operators. So n minus r, and r is this guy, n minus 2. So I have 2 logical qubits. And I can do the same thing with S1 and S2, right? And the reason why this is because now we don't have this non-trivial loops in the stabilizer group S0, whereas in the original Kitaev model, you have this non-trivial loop in your stabilizer. And that's precisely what becomes our logical operators. So if I just flatten out like this honeycomb lattice, now I can have this pair of logical operators. You have another pair there for the second qubit, but just for purpose of this tutorial, you can have like this horizontal and vertical logical operators, right? Um, and yeah, so this LV and LH, right? So LV will be the one going that way, and LH will be the one going that way. So if I just look at this guy, right? So say this is round 0. Um, and then I measure X. I see that that commutes with this vertical operator because they only have X's on them, right? So I use rule 2 and just keep this vertical operator up to some stabilizers, right? Because like all the X checks now in my new stabilizer S1, I can just multiply that to my LV. So that's why we have like this new vertical operator here, but they're the same thing. And sort of like this should be Z check. Oh no, that's an X check. Yeah, so that's correct. So this LH, so they have this Z it has Z's on it, but if you see here like it coincides with 2 qubits um with the checks over like 2 qubits, so like they also commute with each other. But the reason why we want to pick like this Y here is that because I can multiply this Z's with the X checks because they're in the stabilizer. um so that just, that we kind of like pre-updating logical operators so that this y's kind of like commute with this y measurement in the next round. So it's just like a matter of like, whether you want to pick a nice logical representative before you do your next measurement. Um, but yeah. Yeah, I guess that I was planning to go over some examples, but I think this is plenty enough for now. Just going to do that next week. Yeah, yeah, I think I'm gonna skip this. I mean, you could I'm gonna share this slide, and if you wanna like um do this as an exercise, how to update from one round to the next, and what are the stabilizers, and what are the syndromes that you get. Yeah, I'll go through this in the next next week in detail. Yeah, and that's some citations. Thanks.
Yeah. Okay. Thank you, Andrew. It's a fantastic talk. So anybody have any questions here regarding the talk? You can either unmute yourself or type something in the chat box.
Haven't
Okay.
Okay.
So can I have one naive question here?
Yeah,
Like
yeah.
if you measure like a check P, so how do you guarantee that the product of G1, G2, or G1, G3 something they commute with the P here? Maybe I didn't follow it very closely.
Yeah. Yeah, sorry, I should have explained that more clearly. Okay, so I'm gonna take this subset of the generators, right? This W. So this is a subset of the original generator that generates this S.
Uh,
Um, so P anti-commutes with each of this G1 through GL, right?
yes.
So
Okay.
GJ P is equal to
I,
minus
s- I see. I see. Okay.
GJ.
So the whole group of W just anti-commute with P.
Yeah, yeah.
Okay.
So this is all generators
I see. I see.
that anti-commute with P. I put those in W. So I collect all of them. So the rest of G is commutes with W.
Okay, cool. Thank you.
So yeah. So that's clear, right? So if I put like this
Yes, it makes
G1
sense.
there and G1 there, so that gonna cancels out this negative.
Okay. So if anybody doesn't have any questions here, so we can stop here. So thank you, everybody. Thank you, Andrew.
Thanks.
Yeah, thank you. See you next week.